10,
let's go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
Every civilization, from the first humans who gathered around crackling fires to the engineers guiding spacecraft across the void, has asked one question so simple yet so impossible. How far can we go? So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together, not in imagination, not in dreams, but in reality, with the tools we have right now, because for all our ambition, for all our visions of interstellar empires and distant suns, humanity is still a young species standing at the shoreline of a cosmic ocean, dipping only our toes into the waves. We speak boldly of galaxies and light years, yet we have barely learned to leave our own planet, and still, we reach. We always reach. We build rockets, satellites, telescopes, stations suspended above Earth. We send probes toward distant planets and beyond the sun's influence. We climb, step by step, toward the stars, even if they remain forever out of reach, for now. But before we draw maps to Alpha Centauri or dream of voyaging across the galaxy, we must face a truth more humbling. How far can humanity actually travel through space today? With the technology we possess at this moment, not the engines of tomorrow, not the fantasies of science fiction, but the rockets, probes, and ships we can launch in this very hour. To answer that question, we must begin not with the stars, but with ourselves, with Earth, our cradle, our cage, our launch pad. We spend our entire lives within Earth's atmosphere, held down by gravity's invisible chains. Every rocket, every spacecraft, every experiment begins with a battle, a violent, fiery struggle to break free from the pull of our own world. Reaching orbit is not a journey outward. It is a journey sideways, incredibly fast. So fast you fall around the Earth instead of back to it. To climb higher, to the Moon, to Mars, to the planets scattered across our solar system, requires a victory over physics itself. Humanity's greatest triumph is not traveling through space. It is the ability to escape Earth at all. And we've only been doing that for a few decades. The first humans who looked up at the stars could not imagine what we see today. Space stations orbiting above us, probes drifting into interstellar night, rovers crawling across alien landscapes, telescopes capturing light older than Earth itself. But these miracles did not take us far. Space is deceptive. Distances seem close on paper, 1,000,000 kilometers here, 1 billion there, but in reality, they stretch into eternity. If Earth were a grain of sand, the Moon would be a thumb width away, Mars a few meters, Jupiter a house down the street, and Alpha Centauri, another grain of sand, in another country. Despite all our brilliance, all our innovation, all our courage, the truth is harsh. We have barely moved. But what we have achieved marks the beginning of something greater. Let us start with the most advanced travelers of all, us humans. Our bodies are fragile. Our ships are delicate. Radiation kills, microgravity weakens us, isolation consumes us. And yet, we went. Between 1968 and 1972, the Apollo astronauts became the only humans in history to break Earth's protective embrace and journey into deep space. They traveled to the Moon, 384,400 kilometers away. That is the farthest human beings have ever ventured. 50 years later, we still have not gone farther. No humans have left Earth's neighborhood since. No humans have approached another planet. No humans have crossed the invisible boundary where the sun's gravity loosens its grip. Our species, the species that dreams of galaxies, is still tied to the Moon, like a child refusing to leave the doorstep. If humans cannot yet cross the void, our machines can try. And one machine, more than any other, tells us the truth about our limits. Voyager 1. Launched in 1977, built with the simplest computers and oldest engineering of the space age, it has traveled farther than any object humanity has ever created. Today, Voyager 1 drifts in the space between the stars, interstellar space, over 24 billion kilometers from Earth. That is roughly 140 astronomical units, 0.0025 light years, 20 light hours. Voyager 1 is moving faster than any other spacecraft we've ever launched. Yet even at that speed, if it were aimed at the nearest star, it would take more than 70,000 years to reach it. 700 centuries, longer than the entire history of human civilization. That is the distance between us and the stars, a distance no rocket today can hope to cross. So, how far can we travel through space right now? Not very far. Not compared to the scale of the universe. We can reach Earth orbit, the Moon, Mars with robotic probes, the outer planets with decades-long missions, the edge of the heliosphere with 50-year-old spacecraft, but we cannot reach the stars. We cannot escape the solar system in any meaningful timescale. We cannot cross a single light year with the engines we currently possess. If the Milky Way were the size of Africa, humanity has traveled the distance of a single step. This is our reality. This is the starting point of our cosmic journey. The story does not end with limitation. It begins with hunger. A hunger to go farther, faster, deeper into the dark. Because humanity has always lived at the edge of the impossible. We were not meant to fly, yet we did. We were not meant to leave Earth, yet we did. We were not meant to explore the planets, yet we did. We were not meant to dream of the stars, yet we do. This section marks the beginning of the truth. We are small, our reach is short, our engines are weak, but our ambition is infinite. And the question becomes, not how far can we travel right now, but how far will we travel next? Every great journey in human history begins with a threshold. For ancient sailors, it was the shoreline. For early explorers, the horizon. For pioneers crossing continents, it was the borders of the known world. But for us, for humanity standing in the modern age, the threshold is something far more powerful, far more unforgiving, and far more expensive. Escaping Earth itself. To understand how far we can travel through space right now, we must understand the machines we rely on. The engines, rockets, and fragile structures that claw their way out of Earth's gravity and push us into the black. Because before we talk about stars or even planets, we must confront the brutal reality. Space begins only when our machines win a war against physics. And that war is fought every single time we launch. If someone who lived 1,000 years ago could witness a modern rocket launch, they would believe we had stolen fire from the gods themselves. A rocket is not a vehicle. It is a controlled explosion. A skyscraper of metal, fuel, pressure, and heat that tears itself free from the grip of a planet. To rise into the sky, a rocket must generate enough force to counteract Earth's gravity, Earth's atmosphere, friction, drag, its own massive weight, and it must do this perfectly, precisely, without hesitation. Every mission, from carrying humans to orbit to sending probes toward the edge of the solar system, begins with this violent leap. But rockets do not take us far, not by cosmic standards. They only take us away from Earth to the next stage of the journey. Once a rocket reaches orbit, something miraculous happens. The violence stops. Silence takes over. The ship floats. Earth curves beneath you like a living marble. Blue, white, gold. Space spreads around you like an endless ocean. But orbit is not far. Orbit is barely stepping out of the driveway. The International Space Station, for example, orbits at 400 kilometers above Earth. That's the distance from Accra to Kumasi. Humanity calls it space, but compared to the solar system, compared to the galaxy, it is nothing. Orbit is simply the platform, the launch pad for everything else. the place where rockets stop and spacecraft begin. Because to go farther, to the moon, to Mars, to deep space, we need machines that can leave orbit behind entirely. Once a spacecraft has escaped Earth's gravity, its purpose changes. It no longer needs brute force. It needs precision. It needs endurance. It needs time. Decades of it. Humanity's spacecraft fall into three categories. 1. Crew vehicles, human travel. Capsules designed to keep fragile bodies alive. NASA's Orion, SpaceX's Crew Dragon, China's Shenzhou. These are durable, but limited. They carry people only short distances. To orbit, to the moon, perhaps one day to Mars. 2. Rovers and landers, planetary exploration. Machines that crawl or rest on alien surfaces. Perseverance on Mars, Chang'e on the moon, the upcoming Mars, sample return missions. They travel far after arriving, but cannot travel far through space. 3. Deep space probes, our true explorers. These are the ships that define our limits. Voyager 1 and 2, New Horizons, Pioneer 10 and 11, the upcoming interstellar probes. They navigate the solar system and beyond with patience, precision, and painfully slow speed. These are the machines that show how far we can truly travel today. Here is an uncomfortable truth. Humanity has not yet built a spacecraft capable of reaching even 0.01% the speed of light. The fastest spacecraft ever launched, Parker Solar Probe, reaches 700,000 km/h, an astonishing speed by human standards. But still, 0.064% of light speed. It would take 6,500 years to travel 1 light year, and over 200,000 years to reach Alpha Centauri. This is our limit. This is our fastest machine. This is the truth of our cosmic reach. Light-year distances laugh at us. Let's break down the reality. Humans can travel to orbit, to the moon, possibly to Mars in the future. That is the boundary of human travel. Rovers and robots can travel across planets, over moons, inside asteroid belts, but only after being delivered there by rockets. Space probes can travel across the solar system, into interstellar space, but slowly, painfully slowly. Voyager 1 is the ambassador of human ambition and the evidence of our limits. Launched in 1977, powered by technology older than your grandparents, it has reached interstellar space over 24 billion kilometers away. It is the farthest object humanity has ever sent anywhere. But even at its speed, it will not reach another star for 70,000 years. That is the reality of what we can do right now. Imagine the solar system as a giant stadium. Earth's orbit is a tiny circle at the center. Neptune is the last visible row. Voyager 1 has just stepped outside the doors. And the nearest star? It's another stadium 4 cities away. This is the scale we face. This is what our current technology struggles with. This is why traveling through space today is not a voyage. It is a slow drift into darkness. Every machine we send is a lesson. Every failure is a guide. Every success is a platform for something greater. Humanity's current travel capabilities are tiny, fragile, and slow, but they are ours. They mark the beginning of a future where the universe becomes reachable. And the story of how far we can travel today is not a story of limitation. It is a story of beginnings. A story of machines we built with trembling hands, thrust into a darkness we barely understand, reaching distances our ancestors could not have imagined. Every generation imagines itself standing on the brink of something greater. But when it comes to traveling through space, humanity isn't standing on the edge of greatness. We're standing on the edge of a very, very small island, staring into an ocean so vast that even our bravest machines look like drifting specks of dust. Yet that tiny island, as fragile as it is glorious, represents the full extent of what we've achieved so far. So how far have we truly gone? How far can we go right now with the technology we actually possess? To understand our limits, we first have to understand the explorers we've sent before us. The silent, tireless probes still drifting outward at unimaginable distances. The most distant human-made object in existence is Voyager 1. launched in 1977. When it left Earth, the world was a different place. No smartphones, no internet. The Cold War still cast shadows over continents. And yet, we built a machine that would one day leave the solar system behind. Today, Voyager 1 is over 24 billion kilometers from Earth. A distance so large, it becomes meaningless unless we translate it. It takes over 22 hours for a radio signal traveling at the speed of light to reach it. It's moving at 17 kilometers per second, fast enough to circle Earth in 40 minutes. And yet, in the scale of the galaxy, it has barely taken a single step outside the door. Voyager 2 follows behind, a little slower, a little closer, still drifting through the dark like a bottle tossed into a cosmic ocean. But here is the humbling truth. It took nearly 50 years to get them this far. And they have only just exited the boundary, known as interstellar space. For all our brilliance, all our innovations, all our ambition, this is the limit of humanity's physical reach at this moment. Humans have traveled far less. The farthest any person has ever been from Earth was during the Apollo 13 mission, when the spacecraft swung around the far side of the Moon. Maximum distance, 400,000 kilometers. That's it. In a galaxy 100,000 light-years wide, the farthest humans have journeyed is a fraction so small that if the Milky Way was scaled down to the size of the African continent, the entirety of human exploration wouldn't even reach the thickness of a sheet of paper. We are, for now, prisoners of biology and energy. Our bodies cannot endure decades in space. Our rockets cannot accelerate us fast enough. Our fuel is too heavy, too slow, too primitive. So instead, we send our robots into the dark, hoping they will go where we cannot. What is the fastest spacecraft ever launched? Not Voyager, not New Horizons. The champion is Parker Solar Probe, launched in 2018. A spacecraft that dives dangerously close to the Sun and slingshots around it at unimaginable velocities. At its peak, Parker travels at 700,000 kilometers per hour, 190 kilometers per second, 0.064% the speed of light. Fast enough to travel from New York to Los Angeles in 20 seconds. Fast enough to orbit Earth in under 10 minutes. And yet, at this speed, it would still need 6,500 years to reach the nearest star. The speed of light isn't just fast. It is so fast that even our most advanced engineering looks like crawling. This is the uncomfortable truth of space travel as it exists today. We can travel fast, but we cannot travel far. And we certainly cannot travel fast for long periods of time. Chemical rockets, the ones we currently rely on, are powerful enough to escape Earth, but too weak for interstellar voyages. Ion thrusters, efficient and futuristic, push for years but with the strength of a sigh. Nuclear propulsion, promising on paper, remains locked behind political and engineering obstacles. We are like early sailors with crude boats, staring at the horizon, knowing land exists somewhere beyond the waves, but unable to reach it with the vessels at hand. If we had thousands of years, we could reach other stars with today's speeds. But human lives are short. Technology evolves slower than our ambitions, and space is unimaginably vast. This is the cruel mathematics of our era. Voyager 1 will reach the distance of 1 light-year in 17,700 years. It will pass near another star in 40,000 years. Humans cannot survive such journeys. Not yet. We can send machines into the void, but we cannot follow them. Not now. So how far can we travel through space right now? Here is the honest answer. We can explore the solar system with robots. We can explore the Moon and Mars with humans. We cannot travel to the stars. Not yet. Our reach ends where our ability to generate sustained speed ends. Our dreams extend far beyond the limits of our engines. Every species is limited by the tools it creates. The cheetah is bound by muscle, the eagle is bound by wings, and humanity, for all our genius, is bound by the engines we have built. We dream of traveling to the stars, yet the machines we rely on whisper a sobering truth. We are still using the same fundamental propulsion technology invented in the 1940s. Fire, Fuel, expansion, push, crude, heavy, inefficient, and hopelessly slow when compared to the distances of space. If we want to understand how far we can travel right now, we must understand the invisible chains that tie us to our cosmic backyard. These are the giants that take us off the ground. Saturn V, Falcon Heavy, SLS. They roar, they thunder, they claw at the sky with violence and fire. But once they escape Earth, their power fades. They are sprinters, not marathoners. A chemical rocket can get a spacecraft up to 8 kilometers s to orbit, maybe 12 to 17 kilometers s if you burn all your fuel, and then nothing. No more thrust, no more speed. Just coasting. In space, speed is survival, and chemical rockets simply cannot maintain it. That is why Voyager, Pioneer, New Horizons all needed gravitational slingshots, cosmic catapults, to push them further. We steal momentum from planets because we cannot make enough ourselves. The first barrier to interstellar travel is painfully simple. We don't have engines powerful enough to accelerate us for years. Space is cruel because everything you need, you must carry. Water, food, air, radiation shields, habitat, and most importantly, fuel. But fuel has weight, and to carry fuel, you need more fuel. And to carry that fuel, you need even more fuel. It becomes a spiraling paradox that engineers call the tyranny of the rocket equation. This single equation quietly rules everything we can or cannot do. The more fuel required, the more impossible the trip becomes. If we tried to travel to the nearest star with chemical rockets, the fuel tank would need to be larger than Earth. Literally, we are trapped by mass, a prison built from physics itself. Even if we could build a rocket that travels at the speed of Voyager, 17 kilometers, we face a more human limit. A journey to Alpha Centauri at that speed would take 75,000 years, 75 millennia. Civilizations rise and fall in that time. Languages die, coastlines shift, species evolve. No living crew could survive that. No generation ship has ever been built. No human institution has ever lasted that long. Our biology refuses to match the scale of the cosmos. Time is the enemy. Time is the wall. Time is the reason we cannot go far. Humans are fragile creatures. We need constant heat, breathable air, clean water, nutritious food, and a shield from radiation so violent it would shred DNA like paper. We evolved under a blanket of atmosphere and magnetic field. Leave that blanket, and space becomes a silent predator. A ship traveling for decades, let alone centuries, must recycle air perfectly, recycle water endlessly, sustain crops in zero gravity, repair itself, protect the crew from cosmic radiation, shield them from solar storms, maintain artificial gravity, avoid psychological collapse. Even the International Space Station, only 400 kilometers up, struggles with these problems. Imagine doing it for decades, for centuries, for millennia. Right now we cannot. Life support is the quiet killer of interstellar dreams. Everything in space requires power, heating, cooling, navigation, communication, radiation shielding, propulsion.
Booster ignition,
Solar
liftoff,
panels work
Space Shuttle
near the
Discovery.
sun, but the
Taking
farther
the
you
space
go,
station to
the
full
dimmer the
power
light
for full
becomes.
science.
Past Jupiter, sunlight is so weak that traditional solar power becomes nearly useless. Nuclear power helps. RTGs like those on Voyager use plutonium to generate heat and electricity. But we cannot build reactors large enough, safe enough, and light enough to power interstellar engines. Even if we solved propulsion, energy would still choke our ambitions. This is the chain no physicist wants to talk about. But it is real. Technology doesn't advance in a vacuum. Nations fund what benefits them. Companies invest in what profits them. No government wants to build a ship that takes 200 years to finish a mission, because no politician can take credit for it. Space exploration has always been controlled by the forces of economic pressure, military competition, political cycles. The Apollo missions ended not because we lost interest in the moon, but because the geopolitical incentive faded. Interstellar travel will not happen until humanity decides, collectively, that the stars are worth the cost. Right now, we are not there. There is a final chain that does not come from physics or engineering. It comes from us. Humanity has spent more time imagining starships than building them. We have drawn them in art, written them into stories, simulated them in movies. But reality remains painfully grounded. We love the idea of traveling to the stars, but we fear the cost, the sacrifice, the uncertainty, and so we dream instead of doing. We fantasize instead of building. We imagine instead of launching. The greatest barrier to interstellar travel is psychological. Will we choose to remain a planetary species, safe, small, cautious? Or will we decide the unknown is worth the risk? And so we arrive at a difficult truth. Humanity is not held back by a single problem. We are held back by an entire ecosystem of limitations. Propulsion, fuel, biology, energy, politics, psychology, all of it forms a trap, a cage woven from physics and human nature. But like every trap humans have encountered in history, it is not permanent. Chain by chain, century by century, idea by idea, we are breaking free. Every limitation humanity faces in space has a potential escape route, though few of them are easy, and none are cheap. While today we drift in the solar system at painfully slow speeds, the seeds of tomorrow's interstellar travel already exist in labs, white papers, and the minds of visionary engineers, where the impossible ideas of science fiction inch toward plausible engineering, where the chains of Section 4 might be broken. Chemical rockets are powerful but fleeting. Nuclear propulsion promises endurance and speed far beyond our current engines. Nuclear thermal rockets, NTRs, use nuclear reactors to heat propellant instead of burning fuel chemically. Could double or triple the efficiency of traditional rockets. Could reduce Mars transit from 6 to 9 months to 3 to 4 months. Nuclear electric propulsion uses a nuclear reactor to generate electricity, powering ion engines. Extremely efficient over long periods. Acceleration is slow, but it can continue for years, allowing spacecraft to reach unprecedented speeds. The advantage: nuclear propulsion is not bound by the tyranny of chemical fuel mass. It allows spacecraft to carry less fuel and more payload, or travel faster for the same fuel. The challenge: radiation, reactor safety, and politics. Launching nuclear reactors into orbit is controversial to say the least, but the payoff is massive. The first human missions to Mars using nuclear rockets could arrive faster, safer, and with more cargo. Imagine a ship with no engines, no fuel tanks, no propellant, just a giant reflective sail pushed by sunlight. Solar sails leverage the momentum of photons, tiny particles of light, to accelerate spacecraft over time. Individually, photons push weakly. Collectively, over years, they can build incredible speeds. Examples: Ikaros, Japan, deployed in 2010, demonstrated solar sailing in interplanetary space. LightSail, USA, launched 2015 and 2019, showed that sunlight could move a spacecraft. Potential: speeds up to hundreds of kilometers per second over years. Could propel probes to the outer solar system without fuel. In combination with laser arrays, could theoretically reach 10 to 20% the speed of light, fast enough to reach nearby stars within a human lifetime. Limitations: requires extremely large sails, hundreds of meters. Acceleration is slow. Navigation and steering are delicate. Still, solar sails may offer the first practical route beyond our solar system. Energy is the fuel of motion, and antimatter is the ultimate energy reservoir. When antimatter meets matter, the reaction converts 100% of mass into energy, far more efficient than nuclear fission or fusion. Potential: speeds approaching 50 to 90% of light speed. Could reach Proxima Centauri in decades instead of millennia. Challenges: antimatter is extremely rare and difficult to store. Even micrograms could destroy a spacecraft if containment fails. Technology is still experimental, decades away at best. Antimatter propulsion is not science fiction. It's a distant, dangerous possibility. Theoretically, it is the key to breaking the light-speed barrier that holds humanity captive. Fusion, the reaction that powers the sun, promises incredible energy density. If harnessed for propulsion, fusion engines could provide continuous thrust over years or decades, reach 10 to 20% light speed with advanced designs, power both propulsion and life support simultaneously. Projects and proposals. Project Daedalus, 1970s. Conceptual probe to Barnard's star using fusion pellets. Direct fusion drive, USA, 2020s. Early prototypes show fusion engines could be feasible within decades. Challenges: containing fusion reactions safely, building reactors light and small enough for spacecraft, maintaining continuous operation over decades. Fusion propulsion promises practical interstellar travel, but humanity is still in the first chapters of building it. Breakthrough Starshot, announced in 2016, is one of the boldest proposals in modern physics. Tiny wafer-scale probes pushed by Earth-based gigawatt lasers could reach 20% the speed of light, travel to Alpha Centauri in 20 years. The concept sidesteps the fuel problem entirely. The spacecraft carries no engine. The push comes from lasers fired across 4.3 light-years. Challenges: maintaining a coherent laser beam over billions of kilometers, protecting probes from interstellar dust, communications across light-years. Still, it represents humanity's first plausible way to send a probe to another star within a human lifetime. Even if we solve propulsion, human travel remains difficult. Enter generation ships, massive self-contained habitats designed for centuries-long voyages. Entire civilizations could live, die, and be born on board. Requirements: closed-loop life support, air, water, food. Artificial gravity, centrifugal rotation, radiation shielding. Social systems capable of surviving generations in isolation. Generation ships may be the only practical way to send humans to nearby stars until propulsion technologies mature. But they require society to commit for centuries, a political and logistical challenge unlike anything humanity has faced. No single technology will carry humanity beyond our solar system. The future will likely require a combination of approaches: nuclear or fusion engines to reach Mars quickly, solar or laser sails for lightweight probes, antimatter or fusion engines for interstellar pioneers, generation ships for humans. Each technology breaks one chain of the trap that confines us today. Together, they offer the first glimpse of true cosmic freedom. Humanity's current travel is painfully slow, restricted, and small, but the seeds of the future are already planted. Nuclear rockets promise speed and endurance. Solar and laser sails promise fuel-free acceleration. Fusion and antimatter offer near-light speeds. Generation ships offer survival across centuries. Today, we drift across the solar system. Tomorrow, we may sail between stars. Space is not merely a vacuum filled with stars. It is a testing ground for the limits of human endurance, ingenuity, and spirit. Every probe we send faces the cold, the darkness, the radiation, and survives because it requires nothing but circuits. Humans are different. Flesh, blood, and mind tether us to the rhythms of Earth. Send a human beyond the Moon, Mars, or even the asteroid belt, and suddenly, physics is only half the challenge. The other half is human nature. Even low Earth orbit, a short 400 kilometers above Earth, strains the human body. Muscle atrophy. In microgravity, muscles weaken quickly. Astronauts lose 20% of leg and back muscle strength in weeks. Bone density loss. Bones can lose up to 1 to 2% of density per month, risking fractures and long-term osteoporosis. Radiation exposure. Beyond Earth's magnetic shield, cosmic rays and solar radiation bombard astronauts, increasing cancer risk and degenerative diseases. Immune system changes. Microgravity affects white blood cell function, leaving humans more susceptible to illness. Vision problems. Long-term exposure leads to blurred vision and structural eye changes. If a crew were to journey to Mars, They would face these challenges for months. To reach the nearest star, these problems scale from months to decades, and solutions do not yet exist. Even if humans could survive physically, space imposes psychological limits. Isolation, decades or centuries away from Earth, means no immediate contact with friends, family, or civilization. Confined living. Generation ships may be thousands of tons, but still cramped compared to the open expanses of Earth. Monotony. The same walls, same crew, same artificial environment can erode morale and mental health. Decision fatigue. Long missions require autonomy, leadership, and conflict resolution skills that never get a break. Cultural decay. Maintaining language, traditions, and social cohesion over multiple generations is untested at this scale. History on Earth shows that small, isolated communities often fracture under stress. Multiply this by decades in space, and the psychological challenge becomes nearly as daunting as the engineering challenge. One proposed solution is the generation ship, a self-sustaining habitat that supports multiple generations of humans, closed-loop life support, recycling water, air, and nutrients endlessly. Artificial gravity, usually achieved by rotation, food production, hydroponics, aeroponics, or genetically engineered crops. Cultural continuity. Schools, governance, and social systems designed to maintain knowledge and morale. Generation ships are theoretically possible, but the investment is enormous. Decades of planning, enormous resources, and societal consensus. A misstep in engineering, medicine, or governance could doom the entire venture. The more we understand space travel, the clearer it becomes that robots will always go farther, faster, and safer than humans. Robots survive radiation and extreme temperatures. Robots can function for decades without food or air. Robots do not suffer psychological stress. Humans, by contrast, are slow, fragile, and tethered to life support. Until propulsion technologies improve or medicine and life sciences advance dramatically, interstellar human travel is more aspirational than practical. Space travel is not only a technological endeavor, it is a social one. Large-scale missions require global cooperation, resources, funding, and political will from multiple nations. Long-term vision. Projects lasting decades must survive changing governments and economic crises. Ethical frameworks. How to maintain a small community in isolation, with laws and rights spanning generations. The challenge of human expansion into space is as much about governance, culture, and psychology as it is about rockets. If a crew leaves Earth for centuries-long missions, knowledge must be preserved meticulously across generations. Skills must be taught and refreshed continually. Social norms must adapt to isolation without creating factions or unrest. The failure to maintain culture could result in mission collapse, even if propulsion, energy, and life support succeed. Interestingly, the human mind also offers unique advantages: creativity, problem-solving, and resilience. Astronauts on long-duration missions already demonstrate remarkable ingenuity under stress. Humans can repair, innovate, and improvise in ways that machines cannot. Cognitive flexibility is crucial for deep space missions where communication with Earth is delayed by years. In essence, while robots can go farther, humans bring adaptability, a quality that may be essential when nothing goes as planned. Human exploration is limited by biology, muscles, bones, radiation exposure; psychology, isolation, monotony, social cohesion; society, politics, funding, ethical frameworks. Yet, our intelligence, creativity, and adaptability are our secret weapon. The human future in space will likely be hybrid. Robots will scout and prepare, while humans follow only when propulsion, life support, and social systems are robust enough to sustain them. Every civilization has always measured itself by how far it can see and touch. For ancient humans, it was the horizon. For medieval astronomers, It was the farthest star visible through a telescope. Today, humanity measures its reach not in leagues or kilometers, but in astronomical units, light hours, and light years. And yet, despite all our ambition, we are still confined to a tiny corner of the cosmos. Right now, human spaceflight is limited to low Earth orbit, LEO, up to 400 kilometers, where the International Space Station orbits. Astronauts experience microgravity, radiation exposure, and a closed-loop environment that tests every aspect of life support. Lunar missions. The Moon is 384,000 kilometers away. Only humans have traveled there in the 1960s, 70s. With modern rockets, a Moon mission is a few days of travel, manageable in life support terms. Mars missions. Near future. Roughly 400 million kilometers away, depending on orbital alignment. Current technology allows missions lasting 6 to 9 months each way. Nuclear propulsion may reduce that to 3 to 4 months. Key insight: humans are still limited to our solar neighborhood. Even with the best propulsion today, interstellar travel is beyond reach. While humans remain near home, robotic explorers have quietly traveled far beyond. Voyager 1, launched in 1977, now more than 23 billion kilometers from Earth. It entered interstellar space in 2012. Voyager 2, also launched in 1977, traveled past Neptune and Uranus, now over 19 billion kilometers away. New Horizons explored Pluto and continues outward into the Kuiper Belt. These probes move at 117 km/s, slow compared to the speed of light, yet they are the first humans-made objects to leave our sun's protective bubble, the heliosphere. Reality check. Even at these speeds, reaching the nearest star would take tens of thousands of years. The universe remains overwhelmingly vast. Distances in space dwarf human comprehension. Earth to Moon, 384,000 kilometers, 128 light seconds. Earth to Mars, closest approach, 55 million kilometers, 3 light minutes. Voyager to nearest star. Alpha Centauri is 4.37 light years away, or 41 trillion kilometers. At our current speeds, chemical rockets, millions of years to reach Alpha Centauri. Nuclear thermal engines, hypothetical human-rated, tens of thousands of years. Laser-driven nanoprobes, a few decades at best. Space is enormous. Our reach is mostly technological and temporal, not physical. Even within the solar system, several constraints define our practical limits. Propulsion. Chemical rockets dominate human missions. They provide short bursts of energy, then coast. Acceleration is limited, making long-distance travel slow and resource-intensive. Life support oxygen, water, food, and waste recycling are finite. Microgravity causes muscle and bone deterioration. Radiation exposure increases beyond Earth's magnetosphere. Energy, solar panels are effective near the sun. Beyond Jupiter, sunlight weakens. Nuclear sources are limited and heavy. Communication. Signals to Mars take 4 to 24 minutes. Signals to Voyager take over 21 hours. Interstellar communication would require decades for round-trip messages. Within the next 20-50 years, we may see human missions to Mars, 3 to 6 month travel, 1-year surface mission, asteroid mining missions, robots exploring and exploiting resources, 2 to 3 AU from the Sun, Jupiter Moon exploration, robotic probes to Europa or Ganymede for potential signs of life, outer solar system missions, robotic orbiters or landers exploring Uranus, Neptune, or dwarf planets. Even these missions, though groundbreaking, remain a tiny fraction of the galaxy's scale. Humanity is still in its cosmic infancy. The reality of our reach is humbling. Humans, Earth orbit to Mars, possibly a few 100 million kilometers. Robots, out to interstellar space, tens of billions of kilometers. The galaxy, 100,000 light years across, billions of times farther than Voyager has traveled. This teaches a profound lesson. The universe is not meant to be conquered quickly. Our exploration is a patient, incremental endeavor, each step a monumental achievement compared to human history. Right now, humanity is limited to the solar system for human travel, venturing into interstellar space with robotic probes at snail-like cosmic speeds, confronted with distances so vast that even light years feel unreachable. Yet every probe, every launch, every orbiting telescope expands our reach. We are tiny, fragile, and slow, but we are moving outward, slowly breaking the chains of our planetary cradle. For all of human history, exploration has followed a simple formula: better technology, farther horizons. The canoe became the ship, the horse became the train, the rocket became the spacecraft. But space is different. The distances mock our progress. Even our greatest machines drift like dust motes against a backdrop of cosmic infinity. And yet, humanity continues to build, imagine, and design the engines that might one day break us out of our tiny pocket of the galaxy. Section 9 is the story of those future engines, the propulsion systems that could redefine far and perhaps one day, forever. Right now, our fastest spacecraft, the Voyagers, New Horizons, and the Parker Solar Probe, have one thing in common. They coast. Their rockets burn for minutes, and then they drift for decades. This method is useless for interstellar travel. At these speeds, reaching Alpha Centauri, 75,000 years, reaching the center of the Milky Way, 450 million years, crossing the galaxy, 2 billion years. We need new propulsion, engines that can continuously accelerate instead of releasing one brief burst of thrust. Ion engines are humanity's first true break from the old way of doing things. Instead of using massive chemical explosions, they electrically accelerate xenon ions, produce tiny but constant thrust, run for months or even years. NASA's Dawn spacecraft changed the game. Dawn accelerated for over 2,000 days, something no chemical rocket could dream of. This
10,
continuous push adds up.
CLS go for main
Given
engine
enough
start.
time, ion engines can reach
6,
1490
4,
km/s, more than
3,
twice Voyager's
2,
speed. Travel
1,
times to the outer solar system
and
cut in half.
booster ignition liftoff.
Possible,
Space Shuttle
though
Discovery.
slow,
Taking the
routes
space
to
station
interstellar
full power
space.
for full science.
Still far too slow for true star travel, but ion engines are our first sails across the cosmic ocean. NASA and DARPA are now investing in nuclear thermal rockets, NTRs, a technology that could launch us to Mars in 45-90 days. Here's how they work. A nuclear reactor superheats hydrogen. Hydrogen expands and blasts out the nozzle. Thrust is twice as strong as chemical rockets. Efficiency is 3 times higher. This would reduce crew radiation exposure, shorten travel time, make deep space missions more practical. But even NTRs are slow compared to the dream of interstellar travel. So engineers imagine something far more powerful. Fusion is the engine that powers the stars themselves. If humans could build a fusion engine, we could accelerate for years, reach 10%, 20% the speed of light, travel to Alpha Centauri in decades instead of millennia. Projects like Daedalus and Icarus outlined fusion-powered spacecraft that are kilometers long, carry thousands of tons of fuel, burn fusion pellets using powerful lasers. The challenge? Fusion is still a frontier we haven't mastered even on Earth. But if we do, interstellar exploration becomes a scientific mission, not a myth. Antimatter is the most energy-dense substance in the universe. 1 gram of antimatter, explosive energy of a small nuclear bomb. It converts 100% of mass to pure energy. A spacecraft could reach 50% plus the speed of light. But we face enormous problems. We can only produce nanograms per year. Storing antimatter is nearly impossible. One mistake causes instant annihilation. Still, it's the closest thing to an engine that could make humans a relativistic species, capable of traveling between stars in one lifetime. Instead of fuel, solar sails use photons, laser beams, starlight itself. The Breakthrough Starshot project aims to launch gram-sized probes, accelerate them with a 100-gigawatt laser, reach 20% the speed of light, arrive at Alpha Centauri in 20 years. This would be the first interstellar mission within a human lifetime. Not a civilization-sized ship, just a robotic probe, but a spark is enough to light a fire. Every method beyond chemical rockets requires nearly unimaginable amounts of power. Fusion reactors require star-like conditions, antimatter needs planetary-scale energy, laser sails demand global infrastructure. To travel far, humanity must first learn to harness energies that reshape worlds. This is where the concept of the Kardashev scale enters the conversation. Type 1 harnesses all energy of a planet. Type 2 harnesses all energy of a star. Type 3 harnesses all energy of a galaxy. Right now, humanity is at 0.72 on this scale. We are children playing with sparks, dreaming of navigating the thunderstorms of the cosmos. Even if we build engines that accelerate for decades, humans are soft, fragile, biologically unstable in 0G. Long missions require solutions like rotating habitats that simulate gravity, radiation-hardened crew modules, medical nanotechnology, genetic repair systems. Before we travel to the stars, we must learn to protect our bodies from the void. Traveling near the speed of light unleashes strange effects. Time slows for the traveler. Distance contracts in their frame. Decades become years. Years become months. Fusion or antimatter engines could make relativistic travel a scientific inevitability, not a science fiction miracle. To future star travelers, the galaxy might shrink, not physically, but perceptually. Right now, in labs, universities, and aerospace programs, plasma engines are being tested. Nuclear spacecraft designs are underway. Laser sail prototypes are being built. Fusion research is accelerating. Humanity is taking its first steps toward a future in which far might one day mean a different star, a different galaxy, a different destiny. There comes a moment in every civilization's story when imagination outpaces reality so completely that it becomes prophecy. Humanity has always lived at this edge, the thin line between what is possible and what is inevitable. It is about the end game. What happens when humans no longer travel through space as prisoners of time and distance, but travel with space, around space, and even beyond space itself? This is the chapter where humanity stops crawling and begins to reshape the universe around it. At some point, even fusion engines and antimatter drives will feel primitive. They still obey relativity. They still require fuel. They still take years or decades to cross a single light year. But future civilizations may develop technologies where space bends, time warps, distance collapses. These are the propulsion concepts that don't just break speed limits, they delete them. Physicist Miguel Alcubierre proposed something audacious, a warp drive that contracts space in front of a ship and expands it behind. Inside the bubble, the ship doesn't move, but the bubble does, faster than light. This means no time dilation, no relativistic mass increase, no violating physics. The problem? It requires negative energy, a form of matter that, as far as we know, doesn't exist in usable quantities. But the idea won't die, because it solves everything. Alpha Centauri in minutes, the galactic rim in hours, other galaxies in days. It is the closest thing to becoming a civilization of cosmic nomads. Imagine tearing a hole in the fabric of the universe and stitching two distant points together. A doorway, a shortcut, a cosmic elevator shaft. Wormholes would allow instantaneous travel across light years, exploration of distant galaxies, access to places no engine could reach, but they require exotic matter, stability under enormous gravitational stress, technology that manipulates space-time itself. Even so, wormholes remain the ultimate dream. Not travel, but connection. Before warp drives or wormholes, humanity might attempt something slower but profound. A world-sized ship where entire societies live, evolve, and die between the stars. These ships would be self-contained ecosystems, rotating for artificial gravity, powered by fusion or starlight, designed to sail for thousands of years. The ship becomes a world, the destination becomes mythology, the mission becomes culture. This is not travel, this is migration on cosmic timescales. One day, the limits of biology may be too heavy a burden. Imagine uploading a human consciousness, encoding it into data, transmitting it via lasers or quantum networks, receiving it in a robotic or synthetic body at the destination. This eliminates food, air, radiation risk, physical frailty. A human mind becomes a traveler of pure information. Cross the galaxy in centuries. A digital mind wouldn't age a second. A far future civilization might learn to convert a human body into quantum information, light, energy packets. Then, beam the pattern across space, reassemble it with atomic precision at the destination. It is teleportation, not of objects, but of existence. Distance means nothing to light. If you become light, neither will it mean anything to you. Reaching the true cosmic horizon requires unimaginable power. Future civilizations might build Dyson spheres to capture nearly all energy of a star, Shkadov thrusters to physically move entire solar systems, Matryoshka brains, layered megastructures surrounding stars capable of immense computation. These are not ships, they are civilizational engines capable of moving suns, creating artificial worlds, powering warp fields, opening wormholes. At this point, travel becomes irrelevant. The universe itself becomes flexible. On the Kardashev scale, Type 1 controls planetary energy, Type 2 controls stellar energy, Type 3 controls galactic energy. A Type 3 civilization could traverse the galaxy as easily as we cross continents, rewrite stars, engineer black holes, build galaxy-spanning networks. Distance ceases to matter because the civilization's reach becomes cosmic. One day, humanity may ask questions no species has ever asked. Can we leave the galaxy? Can we escape the expansion of space? Can we survive the death of the universe? Can we create new universes? This is the realm of quantum cosmology, multiverse theories, baby universe creation, energy harvesting from black holes. Travel becomes not movement, but transcendence. Whether humanity remains confined to its solar system or becomes a civilization that reshapes galaxies depends on our imagination and our courage. Right now, we are tiny. We are fragile. We crawl at a fraction of light speed. But the story of humanity has always been the same. We start small, we dream big, and then, somehow impossibly, we build our dreams into reality. The universe is not a prison, it is a map, a treasure, a frontier waiting for the species bold enough to claim it.
booster ignition and liftoff of Discovery.